Jeg tenkte at vi skal holde dette kurset på engelsk, siden Chris er engelsk, og han kommer i hvert fall til å holde sin del på engelsk. Det er videoen mye mer anvendelig også, det kan vises i flere land. Så da slår jeg over til engelsk. Delilah is a project that Chris and I have been working on for more than a year now, and it's soon nearing the completion date. We are getting the board soldered up today. We're getting the gate arrays and most of the components this week, and we can start debugging next week. And Dagfinn has made a drawing for us, and John Lloyd Jones has kindly made a slogan for the Delilah project, trimming response times to the bone. And this is quite appropriate because with Delilah we actually have a good opportunity to hook more terminals up to a system. We can get more performance out, and it's actually one of the few things that will improve ND's products with in large systems with a lot of users in the next 2 years. It's actually the only thing that will improve our performance in the next 2 years. These are some of the features that we are putting on this ND-100 type system. This will be an added, it will have an added performance over the RASC today. That's one of the main goals of the project, and that is done by reducing the cycle time, introducing new technology, and by doing that we have got space for some onboard memory. Some of the objectives of this is also to reduce the component costs of the ND-100 today. The power consumption will, as I'll show you, be significantly lower than the previous RASC CPU, ND-110 CX. And it is, of course, necessary to be fully software compatible with all previous ND-100 models. And unnecessary to say, it can also be used as an I/O processor in 500 systems, which is the main aim for this project. And as introduced on RASC 2, we also got a battery backed up clock on the board. When it comes to added CPU performance, that we aim at getting it 1.5 times as fast as the ND-110 CX by reducing the cycle times. This has been possible mainly because of new technology and not a lot of architectural changes. We also anticipate a lot shorter memory access times because of the memory that is on board. And a simplified cache scheme will lead to shorter buffered write cycles. And I'll show you afterwards how this is done. The onboard memory is available in 2 different options. It's 2 or 4 megabytes DRAM on board. This is configured from address 0. It's fixed in order, you cannot adjust it with a thumb wheel. But if you don't like it, you can disable it completely if it's creates a disturbance in your system. If you want the system without local memory, for example, or if you want memory the local memory to be somewhere else in the addressing range. This is to avoid having a lot of switches and stuff, and also we could provide several configurations, but then we had to put the address decoding in PALs, and we'll have to support a whole range of different models, which is not desirable from a marketing standpoint and also for a handling standpoint. But it is possible, but that's what we've chosen. The memory is dual ported between the CPU and the ND-100 bus, and Chris will talk more about how that is done later on. But in fact, it means that we can have the CPU doing an access in the local memory at the same time as a DMA device is doing a DMA transfer in another memory, either local or multi-port. We are using 100 nanosecond access time devices with fast page mode here. And we also have got parity on that memory, but we have not got error correction on it. This is also done in the new Domino modules. There we also only got parity and no error correction. Other features here. The calendar's power is backed up with a battery, so it's no longer necessary to do an update of the clock. It will be set once and for all, and hopefully it will tick forever in storage as well. We have seen some unreliabilities of the RASC-2 there, so we may want to change the type of battery, or well, we definitely got to make this stable. But we've taken this from RASC-2, and we'll see how that works before we finalize this. The bus bandwidth is 20% higher than RASC, which makes it just as fast as ND-100. The bus arbitration scheme is synchronous on both RASC and RASC-2 and Delilah, and it was asynchronous on ND-100. That's why the ND-100 is faster. It's a true handshake on ND-100. Here it's sampled with a 25 nanoseconds oscillator. And we've done a trick here on RASC-2 that has improved the bus bandwidth, but that's not totally verified yet. So it remains to be seen whether we can, or how we can do this. For the console, we have changed the UART. The old UART was quite a big device. It was 40-pin dual inline package, and it also required a lot of support circuitry that took up a lot of space on the board. So we have now swapped that for the same UART used on Butterfly, and we are not supporting current loop. We're only using RS-232, and that will be done on future systems, on all future systems, for the console only, because it's normally placed very close to the machine, and there's no need for anything else there. That will just add complexity and component costs. The only thing you got to swap there is just the cable then, when you put in a new Delilah instead of RASC and the memory. We will provide a new opcom command called LCS, Load Control Store. This will load the control store and do a master clear. The old command, Mackel, will do a master clear without reloading the control store, as before. The reason for this is that when you use telefix, you don't have the option of pressing the button. You got to do it from a terminal. And then if the system hangs in a way that's difficult to, well, if the control store contents has been destroyed and the system is hanging in some way, you cannot fix it from Telefix with only this command. So you got to call the customer, ask him to press master clear, and that's quite awkward. So we're putting that in. This will lead up to the following possible configurations. We are planning 8 different models. It's 3 parameters that will determine this. It's the fast version, which will be as fast as we can get it, at least 1.5 times the ND-110CX, and we'll also provide one compatible in speed to the old model as we did on RASC. We are also supporting 32-bit and 48-bit floating point format, as we always have done. 32-bit will, as on the RASC, be standard. The memory will come in 2 different configurations, 4 or 2 megabytes. We will not have a version without memory, because it would then introduce about 4 more models here, because this will normally always be of an advantage. If we, for some systems, don't want it, then we got to switch to turn the whole thing off. Any questions about the features before I continue with the technology? We'll go into more detail on the different features later on. The cycle time improvement is mainly because of new technology. This, we've put in 2 new gate arrays in 1.5 micron CMOS. I'll describe them in more detail later on. They will replace the 3 gate arrays on the RASC and several other components in order to put in all the memory. We are using 1 megabit DRAM in single inline modules that are very, very compact. I'll also talk a little bit on that. The static RAM that we can use here have increased performance over the RASC static RAMs used in control store, cache, and page tables and register files. It's also possible to have PALs with increased performance now, although these 2 factors will also increase the cost of the components somewhat, but we'll try to create such a balanced system as possible. We'll use the fastest technology to start with and then see where we can put in slower technology and still get the performance. Or it may be a trade-off. Maybe we don't want the performance. We only want the component cost to be low, but that's entirely up to marketing to decide what we really want here. We also are using new CMOS high-speed, low-power buffers, and that will reduce the power consumption quite a lot on the board. But first, about the gate arrays. The one gate array that we've called Delilah is actually what started this whole project off. It was thought to be a good idea to try this new technology, and we're now using this LSI Logic 10K series compacted array series, both for a multiplier, an integer multiplier on Samsung, and also for one of the other gate arrays on Samsung to be reprocessed to gain performance. This has got a channel-less architecture. Don't know how much you know about gate arrays, but a channel-less architecture means that there's no routing channels on the gate array. It's all packed with gates, and it's 50,000 gates on there. which is quite a lot. On the biggest Samsung gate arrays, it's only 8,000. Out of that, we're only using about 14,000. And the reason for that is that your use of the gate area for the routing, you route over the gates that you route over some of the gates in order to provide for, since you haven't got routing channels. So that's why the utilization is that low. This is a bit lower than we can get, but that will add performance to it because we don't have to make such a long wires. This gate array will come in a 224 pin ceramic package, pin grid array. We'll be getting samples this week, late this week, directly in the UK where we'll do the debugging. It will possibly later come in a plastic pin grid array, but that will need some reliability studies before you can see that. But if we can get that in plastic, that will reduce the component cost quite a lot. This is in 1.5 micron CMOS technology. The Rask and Samsung gate arrays are in 2 micron. This has got a typical gate delay of 0.7 nanoseconds, which is almost half of what you can get on the 7K series used in 110CX and Samsung. And overall, a performance increase of at least 1.5 times the 7K series will be the result. Oops. The price of these components will initially be the same as the ND-110 CX gate arrays. So, but that will be reduced because this is initially when we're not buying so many components, and the price will drop. And the Rask gate arrays we've already bought a lot of, so they are quite low down on their price curve, and we're getting the volumes up as well there. But this is not too bad from a component cost standpoint anyway, because actually they've managed to put quite a lot in that gate array. So it will be a component cost decrease anyway. Because from the ND-110CX, this will contain the MIC, Mach, and Buffalo gate arrays. It will contain the complete interrupt system with the two 2914s. It will contain the trap system, which is implemented on the Rask in 4 PALs, and also a lot of decoding, which contains 3 PALs at least, plus about 20 other MSI, SSI packages in dual inline. So we'll get all of that for free, both in board space and in component cost initially. And at least these are about 200 kroner each. So it will contribute both to performance and to cost. And of course the power consumption, because this new gate array does not use more power than one of the previous ones, than the big ALU gate array, the Buffalo gate array. We have also made a gate array with NEC. That we've called ND-DGA, stands for decoding gate array, which is because this contains mostly decoding logic. This is done with NEC CMOS 4A series gate array. This is an ordinary channeled architecture, same as the gate arrays on Rask and Samsung. And it uses 1400 gates out of 1600. Utilization is much higher here because it's got its routing channels already. This comes in a 120 pin plastic pin grid array, which is the same as the RMIC and RMAC on the RASC. It's directly the same pinning. This is also in 1.5 micron CMOS technology, a little bit slower typical gate delay than the gate arrays from LSI. The way we have used this is that we've taken decoding, we've taken signals to be decoded straight in, the star bits from the microcontrol word we've taken in, and decoded that, clocked it, and then put it out. And then you will get actually a reduced performance compared to PALs. Because gate arrays, even though it's quite a low gate delay here, it will not be very advantageous from a speed point of view to take things in and directly out of gate arrays. So we have anticipated that. We may want to take some signals out of this gate array if they haven't got the right performance, but mostly the decoding signals here do not need to be at high speed in order to make the system at least 1.5 times faster than the RASC. But this will reduce the component cost quite a lot, because the price of this gate array is amazing, only about 50 kroner for a 120 pin package. And that is just the same as one 9403, which is one of the components that we have taken out and put in this gate array. This is a FIFO, an old FIFO used for the UART. No, for the calendar display processor. And this gate array contains from the ND-110 CX the panel FIFO, which is two FIFOs, two 9403s. We got a lot of decoding, that's the name of it. That contains at least 6 PALs and one other package, the 39 package. We've got the panel interrupt all in here, which is the 2913. We've got all the power up and power down of the system, which is about 6 SSI packages. All looks like a rat nest on the RASC. We've also got the refresh control on here, which is about 4 39 packages. And this will dramatically improve the reliability of that area. As soon as we then get it to work, it's just to plug in one component instead of having all that lot to get power fail to work. This whole gate array is connected to standby power, of course, because of the power up thing. But it doesn't use a lot of power anyway. It uses less than, for example, what's used in the power up here initially, probably. We are also using DRAM for the local memory on board here. The 4 megabytes on board, we are using 1 megabit devices with 100 nanosecond access time with fast page mode to make easy RAS and CAS implementation. We are using single line packages or modules with 4 of these devices mounted on one side and 5 on the other. And this can make these packages in low profile so that they can be fitted vertically on the board. and you can still have the same spacing between the boards as on the ND-110. These single line packages are small enough so that it can be fitted into the spacing between the boards in an ND-100 system. But we're a bit doubtful if it will fit on the multi-port, because it's a third of a millimeter or something smaller between the card cage positions there. But this has created quite an interest within the company to use those packages. It's about 16 times more compact than the 256K DRAMs on the existing 2 megabyte board for the ND-100. It's 4 times more compact than the 8 megabit board using 1 megabit devices in dual inline packages. And it's also 4 times more compact than the memory on the Butterfly, because we're using almost the same packaging technology as the Butterfly, but we've got 1 megabit devices instead of 256. We are also using static RAM. We use that quite a lot on the ND-110 also. We're using the same packages for the control store on this as the ND-110 CX, but those devices that we used then had an access time of 35 to 40 nanoseconds when we did the design. Now we're getting them in 20 to 25 nanoseconds access times, and that can give also about 1.5 times the 110 CX performance. And if we get that performance out of all the things we do with the system, then we can get a system that's totally at least 1.5 times faster. For the cache and page tables, we used to use 4K by 4s here as well, but we've reduced the cache. That's just half the size of the RASC, so we can use 2K by 8 packages. The page tables were never any bigger. They're only about 1K anyway, the maximum. So we can substitute 4K by 4s with 2K by 8s with also 25 nanoseconds access time. Those were also previously in 40 nanoseconds. Then we will save 8 packages and improve performance. We are also substituting the 1K by 8s for the register file with the 1K by 4s for the register file, 29 something from AMD. By 25 nanosecond access times, 2K by 8. And then we'll also save 2 packages and have improved performance on the register file. PALs with about 30% performance increase is now available. The maximum propagation delay has gone down from 15 to 10 nanoseconds, and that will be available, but it costs 2.5 times as much. So we better be careful with those. We're initially using those all over the place, but we'll see what performance we can get and which ones that can be swapped for normal 15 nanosecond access time devices. But these will also only be of high price the first couple of months. So later on that will even out. It's only about 1 or 2 vendors that's got that already. It's only one that is sampling them at the moment. The CMOS high-speed buffers are quite interesting. It's a small company called Performance Technology, and also several other, both smaller and bigger companies, are currently bringing out high-speed CMOS buffers. These are the same, have the same propagation delay as fast circuits. They can sink the same current, and they've got about 1/3 of the power consumption. Still a high price on those, but that will, with the volumes that we're using, drop dramatically next year or in the next year.